Hello everyone, and welcome to Module 5 of Chapter 12. Was that 5 or 4? Yes, we are in Module 5 this week. In this module, we will be covering Chapter 5, Chapter 12, that is. Chapter 12 is the longest chapter in this course. It's actually one of the longest chapters in the book. The author seems to put in a lot of material into it. A lot of books that would split it into 2 chapters, and that's the reason why I want to cover this chapter in 2 weeks. Typically, when I teach this course, I spend at least 2.5 weeks almost just covering this chapter. Just so much material in it. Anyway, let me go back here. Just to make sure, if you're not familiar with the module 0 here, this is where the course schedule is. It basically tells you up to date what is happening each week. I believe I told you that in the announcement since day 1, but I still get some students who ask me some silly questions like, when is the midterm exam? It's all shown in there. Anyway, if you click on that, so if you go to the course under module 0, course schedule, if you click on that, I am constantly updating this page, and right now we are in module 5. It's a 2-week module, so we're going to cover it in 2 weeks. And once we are done with the second week, which is by May 3rd, okay, we will have a midterm exam. Do you see that right there? The midterm exam is going to open up on a Friday, which is the 1st of May, and it's going to close on the Sunday, which is May 3rd. Let me show you the calendar. May 1st is right here. This is a Friday, and it will close on a Sunday. I haven't done the midterm exam, but basically this is where. So that's gonna be. We are right now. Well, by the time you look at this video, it will be maybe the 20th of April. Today is the 17th. I'm making this video, but anyway. So you have a whole week that you don't need to worry about the midterm until the following week, around the end of the following week, on May 1st. Okay. I'll give you more details on the midterm maybe the following week, because I'm going to be creating another video for the chapter 12. So anyway, keep that in mind, and the midterm is going to cover all the material that we have not covered in midterm 1, and that is chapter 8, 9, 10, 11, and 12. And also, we only have after that really one more chapter, chapter 13, gravitation, and then we will be, done with the course, and then we will be talking about the final exam. And as you know, the final exam is going to be cumulative, okay, but selective. I have no idea how that final is going to be. More details on it later, okay. And I haven't looked up when is the final exam and how is that going to be with this online thing going on. Anyway, more details on that later, okay. Okay, let me go back to the book. Like I said, this is the chapter that we are going to be covering, rotation of a rigid body. It's a long chapter. I am going to be covering the following topics. Actually, seems like he arranged them in opposite order. Next, I'm going to be creating 2 videos. This week, this video, the one that you're listening to, and then around the end of, around the end of next week, or sorry, for your timetable, around the end of this week or the following week, the second week of the module, I will create the second video, okay? But this week I'm going to be covering, I'm looking up the hard copy, it looks better. I'm going to be covering the center of mass, the parallel axis theorem, moment of inertia, and torque. That's it. I mean, basic torque, basic concept of torque. The second week, or the second video rather, I'll be covering torque, more details on torque and angular momentum, okay. And I can cover those two probably in something like 20 minutes, but the rest of the hour I'm going to spend it working on homework problems from the problem from the back of the chapter, mostly homework problems, okay? So my advice to you, start working on the homework problems but do not take the quiz until the end of next week. You got that? Because there is only one quiz, and that quiz is going to be covering, you know, the whole chapter. So wait on the quiz until the end of next week. That's just my advice. Unless you feel comfortable taking the quiz, that's fine. It's really up to you. Anyway, so let's begin. So the first topic I want to talk about in this chapter, and I'm going to be using my my notes more. So the whole chapter is about rotational motion, okay? And we begin, when we talk about rotational motion, the first thing that comes to someone's mind is what we call the center of mass. Let me fix that, sorry. Whoops, it's pink. Center of mass, let me make it black. I just finished another video lecture from another class, and I was using pink for some reason. Anyway, okay. So center of mass, what is? I'm sure you know what the center of mass is. For example, if you have a rod, for example, like that, a homogeneous rod, you know that, you know, say a homogeneous, or like say a pencil, you can balance the pencil on your finger, and this, because you know the center of mass somewhere right there in the middle. You know, just like you have a meter stick, and a meter stick reads from 0 centimeter to 100 centimeter. So the center of mass is not exactly, but somewhere pretty close to 50 centimeter mark, correct? If I have a triangle, let's say something like that. Let's say I have a piece of metal that is triangular in shape. The center of mass is going to be somewhere around here, you know, closer to the base, if you will, and so on, okay? So what is the definition of a center of mass? Here is a definition for you. If you would take any body at all, even a body that looks like that, okay? Let's say you have this random shaped body, a potato shape or something. And if I would take this body and have it rotate freely without any constraints, okay? So I'm going to have the body, let's assume this body is floating in space, okay? And then I just give it a little kick here, okay? Just give it a little kick. So what's going to happen, the body will start rotating. I'm going to use my mouse. Will start rotating around, okay, freely. I'm not forcing it to rotate in a certain way. This rotation will always be a rotation about the center of mass of that body. Let's assume the center of mass of the body is right here. So it's going to be rotating about the center of mass here. For the case of a triangle here, so if this triangle would be rotating, it's going to look something like that, about the center of mass. If it's going to be rotating freely, that is, of course. Okay, let's assume it's rotating in that fashion, like that. And it's going to go like that. You see what I'm saying? So the center of mass is a point where the body rotates around it, if it is given the opportunity to rotate freely, with no forces, no constraints, nothing, okay? No net force on it, if you will, in equilibrium. All right, okay. How do we calculate it? Well, here is how you calculate it. I'm not gonna cover the integration part of it. The book talks about how to cover it, how to calculate it for extended bodies. We're not gonna do that. I would have covered it if we were, you know, going to classes and stuff, but I'm not going to cover it here. It's just a little bit hard for some of you. So I'm just going to cover the basic parts of it. And that is, let's assume, for example, I'm going to give you, I'll just make up an example and I'll show you how that works. Let me draw XY coordinates here, like this. Let's assume that I have a point here. Let me make it big. Here's another point, and another point here. And let's say I have another point here. Let's say here, okay? And each point, let's make them masses or something. Each one has a certain mass. Let's assume the mass of this one is 1 gram, 1 ounce, whatever you want, okay? So we'll make it M1. And this is M2, we'll make it 2. M3, let's make it 3, and M4, let's make it 5, okay? And what is the location of this M1? Let's make a calibration here. Something like that. 1, 2, 3, let's say 1, 2, 3, 4, is that right? And then this one, 1, 2, and this is 1, 2, and then this one 5, 6, 7, 8. Let's make this 8, okay? So the coordinate of this point, M2, would be 8, 0. The coordinate of this one would be 2, negative 2. Are you following me so far? M1 would be 4, comma 3, and M4, let's make it 4 just for consistency. That'll be negative 2, comma 0, correct? If I want to find the center of mass, here's how they calculate the center of mass. Well, the center of mass is going to be somewhere. I don't know. Let's assume it's here somewhere. Okay, do you see where the mouse is? Let's assume there. I don't know where. So how do I calculate that? Well, here's how it works. The formula is this. You have, since we said that the point, let's say, is here, so that point would have x and y coordinates. So I'm interested in finding the x and y coordinate of that center of mass. You got that? Okay. So I do that. Here's how it works. So you have x sub cm would be equal to, here's the formula for it, m1 x1 plus m2 x2 plus m3 x3 plus m4 x4. We happen to have 4 of them. Okay, if we have 5, we'll make it another one. And then divided by the sum of the masses. Got it? Same thing with y sub cm. m1 y1 plus m2 y2 plus m3 y3 plus m4 y4 over the sum of the masses. m1 plus m2 plus m3 plus m4. Got that, guys? So let's get x sub cm. I need to lift it a little bit. Okay. All right, let's do it quickly. Nothing difficult about it, as you can see. So we start with m1. So I have the mass is 1 kilogram, 1 gram, whatever, times the x1 would be 4 plus m2 is 2 times 8 plus 3 times 2 plus m4 is 4 times negative 2. You got that? The total mass is 1 plus 2 plus 3 plus 4. That gives me 4 plus 16 plus 6 plus minus negative 8 divided by, what is that? 5, 9, 10, right? So that will be 20. 20 minus 2, negative 18. I think I did it right. And that'll be negative 1.8. This is C sub m, xc sub m, okay? There it is. You box it. Now let me find y sub cm. So again, we just use the formula that you see above right there. So that's going to be 1 times y1, that'll be 3, plus 2 times 0, all right, plus 2 times, oops, hold on. Am I making a mistake? Yeah, sorry, this is 3 here, right? Times negative 2 plus 4 times 0 divided by 10. Okay? Calculate that. That's 0. That's 0. That's going to be 3 minus 6 over 10. So that will be equal to, I hope I'm not making any silly mistakes, negative 3 over 10. What is that? I'm using a calculator. That will be 3 over 10. That's 0.3, right? 0.3. Okay, so this will be negative 0.3. That's ycm. Okay. In other words, the center of mass, which is x sub cm, comma y sub cm, is basically negative 1.8, comma negative 0.3. If I'm going to draw it, let me put a different color. So if I'm going to plot it here, so negative 1.8, which is right here roughly, and negative 0.3 is right here. So the center of mass, if I did it correctly, of course, is right there. That's the center of mass of the system. And there we go. You got it? Okay. me show you another problem from the book. I'll do it very quickly, similar to ours. Example 12.1. Okay. It says, oh, we have the book. Let me go to it. That's in section 2. Oh, here's the equation for the center mass right there. Okay. Equation 12.4, similar to the one I showed you. I think I went too far. One more back. Should be here. Here it is. Okay, so what you have, here's the example 12.1 right there. It says a barbell, which is right there, this picture right here, consists of 500-gram ball and a 2-gram ball. So you have one, this is 500-gram ball, and that's a, 2-kilogram ball. Okay. Okay, so that's would be 2,000 gram. Okay. Connected by a massless 50-centimeter long rod. He wants to know the center of mass, and he wants to know the speed. He said, what is the speed of each ball if they rotate about the center of mass at 40 RPM, revolution per minute? Okay? So let's do that. I'll do it quickly. So I like to put it, I don't know if he has it on X. Well, yeah, he has it on the X-axis. So I like to do that. So it looks something like that. Here is the first ball. Here is the rod that is considered massless. Sorry, it doesn't look straight at all. Let me do it better. And then here we have another ball right there. Okay, I'll call this ball 1, ball 2. This is 2 kilogram, and this is 0.5 kilogram, correct? The length, so if I put an x-axis right there, so this is x equals 0. We'll make it x equals, you can make it whatever you want. And that's x equals half. Why half? Or rather 0.5, right? Because he said in the problem, 50 centimeter, okay? So half a meter, okay? So let's find the center of mass. So there is no y sub cm. You agree with me? Here is 0, because it's all along the x-axis. So x sub cm, you know the formula. Here is the formula symbolically. Sigma sub I, m sub I, x sub I over sigma sub I, m sub I, right? Makes sense if you draw it this way. It looks more elegant writing it this way. But anyway, let's apply it. So we only have two objects. So xcm is equal to, the sum of the masses here is just 2.5 kilogram. You agree with me on that? And then, so we have here 2 kilogram times 0. See the location of it is 0. Plus, and then we have here 0.5 kilogram times 0.5. And so that will be 0.25 over 2.5. And the center of mass, of course, you wouldn't expect it to be right there in the middle. And the center of mass is going to be 0.1, correct? Let me use a calculator. I think 0.25 divided by 0.25 divided by 2.5, 0.1, yes, 2.1 meter. So where would it be if I use red color here? So it's going to be, remember, we start counting from 0 right here. So this is 0.5. So it's a fifth of the way. So roughly, give or take, let's say it's here. This is the center mass right there. Got it? In other words, if I would put my finger here, this thing will balance. Got it? Okay. Next. He has another problem. Look at problem number, example 2. See, he has the integration part for extended bodies. I'm sorry, we're not going to cover it. It's not terribly hard, but it just, I know it's going to be hard for some of the students. So I think you need a live teacher in class working on that. So we're just going to skip that. And then the next topic is, oh, I'm sorry, there is one more part to it. This is why I wanted to do it. The second part of the problem, sorry, let me just finish that. Second part, part B, he said, let me go back. He said, what is the speed of each ball if they rotate here? If they rotate, I already lost it, sorry. He says, what's the speed of each ball if they rotate about the center of mass at 40 revolutions per minute, okay? So we know that it is 40 revolutions per minute. What is that? That's frequency. So frequency is 40 rev per min. Always make it rev per sec, which is hertz. So that's 40 rev per 60 second, and that will give it to me in hertz. So that will be, what would that be? 40, I'm using my calculator here. Please work with me. Divided by 60, answer 0.67 hertz. Okay, now I want to find omega. Well, omega is 2 pi f, right? So 2 pi, 2 times pi, times 0.67, and you work it out, and you will end up getting times 6.28 equals 4.19 radian per second. Okay, let me just make a comment here before I go any further. Let me go back to the drawing. Look, so you get those dumbbells, right? They're rotating. Let's assume they're rotating this way, for example. This way, and then this thing is going, this ball is going this way. So they're going around like that, okay? Around like that. Now, regardless of the radius, okay, this rotation will be the same. In other words, they have the same omega. Got it? Because this is like RPM, revolution per minute, regardless of the radius, they have the same omega. What's different is the velocity, in other words, v. So this v here, v, we call it v2, and this is v1. Those two v's are different. This is very important. So if you see a rotating body, even if the center of mass is not at the center of it's not at the geometric center, if you will, the omega will always be the same for the whole body as it spins, okay? However, the velocity is different. Because why? Because the velocity depends on the radius. Remember, v equals r omega. And here, this r, what is this r? How far is it from the center of mass? So v1 is going to be r1 omega, and v2 is r2 omega, and r1 and r2 are what? This one. Watch, let me put it in a different color. This is, whoop, there we go. This is R1, and this is R2. You got that? So you measure, because the spin is right here, is about the center of mass. So this is the radius as far as this ball is concerned. And this is the radius as far as this ball is concerned. You got that? So R1 and R2 is how far is it from the center of mass. This is very important. So now, easy. So it becomes now V1, it's just going to be R1 omega. Well, what is R1? I know what it is. I have already found the center of mass. The center of mass to be 0.1, correct? And the difference between them, and this distance, excuse me, the distance between them is 0.5. So this R1 in this case is what? Oh, well, it's 0.1. R2 would be 0.4, correct? So this is going to be 0.1 times omega. I just got it right there, 4.19, and that will give me 0.419 meter per second. And then V2 is R2 omega, and that will be 0.4, correct? Times omega, and when you work it out, I'm just copying it from the book, 1.68 meter per second. There we go. In other words, as you can see, V2, this one, this V2, is much greater than V1. You see what I'm saying? Okay, good. That's a good problem. All right, moving on. I want to talk about rotational energy. Rotational energy. Let me explain. I'm sorry. I should have said your book calls it rotational energy. I don't like this term. I would rather call it rotational kinetic energy. It's more explicit. Rotational kinetic energy. Let me explain it to you. Let's say you have an inclined plane. All right. And on the top here, let's say you have maybe you want to tilt your book. Okay, you have the big book and you want to tilt it. So here's a tilted book at some angle. It doesn't matter what angle. Okay, unless I put here an object. Say you put your calculator right there on the top. Okay, so what's going to happen at a certain angle? The calculator will start sliding down. Right. So in the beginning here, the energy of the calculator is all potential energy, and then by the time it hits here, it's all kinetic. You agree with me on that? There's no potential here because the height is 0. You see what I'm saying? All right, fine. But here's the thing. The calculator as it slides, or the block as it slides, so it has a kinetic energy. We call it translational kinetic energy. Okay, translational. Okay. Why do I call it that? Hold on a minute. I'll tell you in a minute. Okay? Now, look at this diagram that I have just explained. Now, compare it to the following situation. Now, I don't have a calculator. I have the same inclined plane, say the tilted book. But now I have a ball here. Okay? I put a ball. Whatever ball. Golf ball or whatever. Okay? And then, okay, so I ask the question, what is the total energy? It's all potential. Because the height is, h, whatever. Same thing here. And then by the time the ball comes here, well, it's all kinetic. There's no potential anymore, correct? Same situation. But what's the difference between the two? The difference between the two is that the ball is spinning. Okay? So what's going on here with the ball is that the ball has two motions, really. The first one, here's the ball. First, it is spinning about its center of mass. That's the first one. And second, it is moving forward as well. Just like your wheel of your car. What does the wheel do? The wheel spins, that's it. And the car, as a result of that, moves forward. The car doesn't spin, it's the wheel that spins. But there are two motions for the wheel here. So this forward motion is what we refer to as translational kinetic energy. The one you are familiar with, 1/2 mv squared. But there is also a rotational part to it. We call that the rotational kinetic energy, K sub r, if you will, okay? And it's equal to 1/2 I omega squared. A different creature, okay? I'm going to derive 1/2 I omega squared for you in a sec, right now. All right. What does that mean and what does I means? I'll tell you in a sec. Imagine I have an arbitrary shape object. Let's say it's a rigid object. There we go, okay? And, of course, this object is made out of masses or particles, right? Infinite number of atoms, whatever you want to call it. So let's pick 3 of them. One here, and one here. Assume that the object, and let's assume hypothetically that let's say that the object is rotating about some point here. Maybe the center mass, maybe not. It's not really important, okay? But let's say that the object is rotating about this point. Like this. There's omega. Okay. So what's going to happen as it rotates, this, I'm going to call those mass 3, mass 1, and this is mass 2. So what's happening here, as it rotates, it's going to go like that, right? This point, this mass, is going to go in this direction. This one is going to go in this direction. and this is going to go in this direction. Instead of saying as it's going around. Okay, that's what I'm saying. Whatever the direction, but there. So this one will have a direction of, call it v sub 3. This is v sub 1, the velocity, and this is v sub 2. See what I'm saying? Like that. Maybe this is not the right direction for it. Maybe I'll go like that. You know, it will all come together in such a way that will produce this rotation. Okay. Now, also, let me just put a different color. So how far is it from the point of rotation? Well, this would be R3, this is R2, and this is R1. You agree with me on that? Okay. Now, if I ask you the question, what is the total energy of the object? Okay? Well, the total energy, kinetic energy that is. So the kinetic energy here is equal to 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus 1/2 m3 v3 squared plus what? You know, the other masses. There is infinite number of masses. I'm just picking 3 here. You see what I'm saying? But we're going to add up all the kinetic energy that contributed, that are all the masses are contributing to. Okay. Now we know that V1 is equal to R1 omega. Remember, this is the omega right here. So I can plug it in here. Remember, omega is all for the same for all of them, right? It's all the same. So here we have the kinetic energy is going to be 1/2 m1 r1 squared omega squared. I apologize. My phone somebody keep sending me messages. 1/2 m2 r2 squared omega squared plus 1/2 m3 r3 squared omega squared plus blah blah blah. You agree with me on that? Okay. Let's continue on with this thing. Just bear with me. Look what will happen. Now what I want to do, see the omega and the half are kind of they're the same thing, right? So what I want to do, I want to take them as common factor. Or I want to use summation notation with common factor. So it's going to look something like that. Sum 1/2 bracket sum sigma sub I m sub I r sub I squared omega squared. Is that right? You agree with me on that? Okay. We define this to be called the moment of inertia. The moment of inertia. Okay? And this moment of inertia is I. So now, the kinetic energy of this body right here is equal to 1/2 I omega squared. Okay, got it? Okay. There is a table in the book that you must be familiar with. You must, you know, make sure you understand it, and that is find the center mass by integration. We're not going to do that. What is that table? That's in section 3. Let me keep going. There it is. Okay, so here is the moment of inertia, the one I just showed you. And the rotational kinetic energy is equal to 1/2 I omega squared. And then there is we're going to do this problem in a second, but I want to show you the table. There they are. Okay, so each object has its own moment of inertia. Okay, for example, a thin rod. Please read them and make sure you are familiar with them. I'm going to go through them right now with you. So if I have a thin rod, and I am rotating about the center of it. Like, let's say you hold a pencil. Go ahead right now, if you have a pencil handy, just hold it. Hold the pencil right from the middle, and then move your finger to rotate it. You can actually rotate it easily. Now take the same pencil. Oh, sorry. So the rotation of the pencil is equal to 1/12, or excuse me, the moment of inertia of the pencil, as it is rotated about its center, is equal to 1/12 ml squared. Got it? Now, if it's rotated about the side, however, it's 1/3 ml squared. If I have a slab or a plane rotated about the center right here, do you see the center rotation? Is 1/12 ma squared. A, where A is the the radius or the diameter of the rotation right here. Okay, a slab about the edge right there is 1/3 ma squared. And then you have a cylinder that is solid, or a disc, 1/2 mr squared. A hoop, mr squared. It's the largest, by the way, as you can see. They all have ma squared, mr squared, but then it's just a matter of different fractions. And then you have the solid sphere, 2/5 mr squared, and a spherical shell is 2/3 mr squared. Okay, good. All right. Let me do this problem very quickly and show you how this works. It said student participating in engineering project designed the triangular widget seen in the figure. The three masses held together by lightweight plastic rods rotate in the plane of the page without the axle passing through the right angle corner. At what angular velocity does the widget have 100 millijoule of rotational energy? Okay? All right. Sounds hard, but it's not. I'll show you how it works. Put that picture. All right. So what you have in here, let me draw the picture. What I have in here, I need to get rid of this phone. 1 second. I'll be right back. Okay. So here is the triangular shape. I'm trying to make it as straight as I can. There we go. And then I have here an object, and another one here, and another one here. This one is 150 gram. I hope you see it right there, right? You see it right there? Okay, I'm copying it from there. 150 gram. This one, 300 gram. And then this one, 250 gram. And this is 8 centimeters. This is 6 centimeters. And then we are rotating it like that. Oh, hold on. It's going out like this. Okay? Like that. He is asking, what is the value of omega in order for the kinetic energy, the rotational kinetic energy, to be equal to 100 millijoule? That's basically what he's asking for. Okay? What is omega? In other words, what is the RPM? To produce, if the energy is supplied or whatever is 100 millijoule. Okay? So one way to do it is you basically write down the kinetic energy for that. So we have three masses. We are ignoring the masses of the rod. So that's just going to be 1/2 m1 r1 squared omega squared plus 1/2 m2 r2 squared omega squared plus 1/2 m3 r3 squared omega squared. Or we could have just done it that way. 1/2 sigma sub I of mi ri squared omega squared. Let's fill it in now. We can just go back and fill up all that, put in the numbers that we have. So that's going to be 1/2. I'm doing this one here. So that's going to be, for the first mass, it's going to be 0.25 times 0.08. Are you following me? This is R right here. This is 8. Plus 0.3 times 0 squared, right? Remember, the rotation I forgot to mention, rotation is right here. It's about the 300 gram mass. I forgot to mention that, sorry. Ooh, that's not what I want. But let me make a different color here. I forgot to mention that. Stupid phone kind of got me confused. Here we go. So this is the center mass here. We're measuring it from here. Okay. Okay, so when we measure it, we measure everything from here, from here, right there. So as far as the 250 is concerned, it is 0.08 meters away from it. As far as the 150 is concerned, it's 0.06 from it, and so on. You got that? And then, of course, as far as the 300 gram, it is 0 meter away from it. So that's just going to be that plus 0.15 times 0.06 squared times omega squared. All of that is equal to what? Is equal to this number, 100 millijoule. 100 times 10 to the negative 3 joule. And that's it, really. The rest is easy. All you need to do is you solve for omega. So omega, in this case, it will be 1.54 revolution per second. And if I convert it to RPM, it's going to be 92 RPM. And there we go. If you want to call it omega or frequency, whatever you want to call it. Maybe I'll call it frequency. And there we go. Got it? Okay, good. Here's a cool example, example number 12.4. Like I said, in the second video, I'm going to be doing problems. For now, I'm just concentrating on explaining the material. What is that thing? 12.4. Oh, okay. Page 301. All right, let's do that. Okay, he says, oh, we need to find it here. I keep forgetting that. It's there it is right here. So it says, let's read the problem and look at this picture as we read it. He said a 1 meter long, here it is, 1 meter long, 200 gram rod is hinged at one end and connected to a wall. Here's the wall right there, here's the hinge. It is held out horizontally when released. So you are holding it like that, and then you let go. So it's going to fall or rotate about, let's say you're holding it with your fingers. So it's going to fall like that. What's the speed of the tip right here of the rod as it hits the wall? Okay? It looks like a simple problem. Well, let's see how we do it. Okay. Again, free body diagram. I can't do the problem without free body diagram. That's just me. I don't know about you, but okay. Here's the rod right here. It's spinning about this point. And now it's going around. Oops, I want it to be circular as much as I can. So here's the rod right here. So he wants the speed right here, right? Okay. Now, first of all, the rod has a center of mass right there in the middle, as the picture showed. Look at that. So the center of mass is right here. What do you want to do when you deal with a problem like that? Always follow the center of mass and totally ignore the shape of the rod. Just follow the center of mass. So as if you're dealing only with the center of mass, okay? So you ask the question, what is the total energy of the rod here, and what's the total energy of the rod here? And equate them together because the energy is conserved, right? That's one thing. Second, there is no translational kinetic energy. There is no 1/2 mv squared. The whole thing is pure rotation, as you can see here. All of that is just rotation. So basically, when I'm holding it here in this situation, the only energy available for me is really potential, which is mgh, or mg. Well, let's assume that my datum is right there. So this height is L, the length of the rod, right? So it's just mgl. Now, when the rod is here, the center of mass, right before it hit the ground, well, it's still at this height, which is L over 2. So that's mgl over 2, plus what? Plus the rotational kinetic energy of the rod, which is 1/2 I omega squared. So what is I here? Well, I here is the rotational, the moment of inertia of the rod about its side. See that? It's not about the center, because you're holding the rod right there. And the rod rotating about its own side. You see what I'm saying? It's right there. This is the picture right there. So I need to go back to the table, and I want to look up the rod about the side, which is right here. Thin rod about an end right there. So this is the moment that I'm going to use, not this one. This one is about the center. This one is about the side. Do you see the difference? Okay. So I'm going to use 1/3 ml squared. Okay. So I go back here. So I have mgl equals mgl over 2 plus 1/2 1/12 ml squared omega squared. Okay. And then the rest is easy. So the masses cancel out. This L cancel out. I end up with G over L, and this is G, right? So that's going to be G over 2. That will be G over 2 equals to 1/24 L omega squared, correct? And so that will be G equals 1/12 L omega squared. Therefore, omega squared is equal to 12 G over L. Unless I made a dumb mistake. I don't like the answer. Is that right? It should have been 3 here. Oh, I am sorry. Sorry, you're probably screaming at me now. The about the side is 1/3, not 1/12. My apologies, right? I hope I didn't confuse anybody. I should have written 1/3. Not one. I actually said 1/3, but anyway, I ended up doing this. Sorry about that. Let me go back here, and I'll do it with a. This should have been 1/3. And we just erase all of that. Everybody see that? I hope I didn't make any other dumb mistake. Let's see. So that's going to be G over 2 here with those two together equals to 1/6 L omega squared. So that will be G equals 1/3 L omega squared, and therefore omega is equal to 3G over L under the root. And there we go. I'm looking at the hard copy. This is what he got right there. Okay, good. All right. And then we just plug it in. And then he said, what is the velocity of the tip? Well, the velocity is equal to what? Omega r. R here in this case would be L, correct? Because that's the distance from here to here, from the center of rotation. So for our case, V for the tip, and that's going to be omega L. So that will be square root of 3G over L times L. And then you plug in your numbers, you'll get the answer. You see what I'm saying? That'd be it. Got it? Okay. Okay, good. The next topic is the parallel axis theorem. How much time have I been talking here? Almost an hour. Okay. One is called the parallel axis theorem. I'm not going to derive it because it is a little bit complicated, but it's a kind of a cool theorem. It's called the parallel, whoops, where am I? The parallel axis theorem. There is another theorem called the perpendicular axis theorem. If you take an advanced mechanics course with me, we cover all that in details. But anyway, what is the parallel axis theorem? Okay, here it is. Let's say, for example, I want to find, I know that. Let's say I have a cylinder, okay? And I want to find, oops, not very good, there we go. And I know that if I have the cylinder rotate about its center, like that, the moment of inertia of the cylinder about the center, which I can look up right there, it's just 1/2 mr squared. You see what I'm saying? Easy. R here being the radius of the cylinder, and of course the mass of the cylinder. Okay, here is the thing. what if I don't want to rotate the cylinder about the center? No. I want to rotate it about the side. Let me show you. Let's say I want to rotate it about the following side. Pick another color. Right here. About this side. You see what I'm saying? Not necessarily the center, about this side, where this side is, let's say, R over 2, or whatever, you know, let's say R over 2, from the center here, and it's R over 2 from the edge. But let's say it's R over 2. Now, I'm rotating it now, not about the center of the cylinder, but about this axis, okay? Here is where the parallel axis theorem comes in handy. Now, it looks like it's complicated. It's like, oh my gosh, how do I do that? Well, here is what the parallel axis theorem says. The moment of inertia, oops, I'll use black again. The moment of inertia, I, about any axis is equal to the moment of inertia about the center, we'll call it I naught for now, plus md squared. What is d? D is basically how far is it from the center, this distance, the axis. You got it? Let me draw a better picture. Here is the cylinder. I'll make just the top of it, okay? Here is the axis about the center, which is I naught. But I'm going to rotate it about this axis right here, right? And this distance is what? D. And this is the I that this I right here is this I right here. So it's going to be about the center plus md squared. So for example, let's assume it is R over 2. It's just going to be about the center is 1/2 mr squared, as shown in the table right there, right here, plus mr over 2 quantity squared. So it becomes 1/2 mr squared, r squared, plus 1/4 mr squared. And that makes it 3/4 mr squared. There we go. I can actually find it. You got that, guys? Okay. Is there an example on this parallel axis? Yeah, this one is cool. Yeah, let's do this. This is an example from my notes. Look at the, I'll show you. Go back to the table here. We said that for a thin rod, the moment of inertia about the center is 1/12, correct? About the side is 1/3. Can we prove that? I mean, how do they know that? Well, let's see. Here, look. Here is the rod right here. And he said about the center, which is right there, about the center, I naught, that's equal to 1/12 ml squared, L being the length of the rod. Now the question is, what about if I want it around the side, right here? I'm acting like I don't know, okay? Let's see if we get actually 1/3, as he's saying here. We can use the parallel axis theorem. It says I about the side is going to be I about the center plus md squared. Well, about the center to me is 1/12 ml squared plus 1/2 m times d squared, which is the length from here to here, which is what? L over 2 squared. So 1/12 ml squared plus 1/4 ml squared, and if you add up those, I bet you're going to get that 1/3. So that's going to be what is that? 1/12 plus 3 over 12. Is that right? ml squared, and that will be equal to 3 over 12. No. 3. That's going to. No, this is true. And that's going to be 4. Sorry, this is going to be 4 here. 4 L squared, and that'll be 1/3 mL squared, exactly what we got right there. Got it, guys? Okay, see how handy this parallel axis theorem comes in? Okay, good. And the last topic that I want to talk about, but I'm not going to do any problem until next time, is the torque. Torque. What is torque? When you think of torque, think of a think of rotation. Think of a force that causes rotation. So a force that causes rotation, or maybe you can say it's the rotational. Let's say the rotational equivalent of force. Another way of saying it, it is the ability to cause rotation. Okay, whenever you hear the word torque, think a force that causing the object to rotate. The simplest one is basically when you open the door of your bathroom. What happens to the door? Does it move in a straight line? No, it rotates about the hinges. So you are applying torque. This torque, okay? So let's say, for example, let's say you have a rod, for example, laying down on the floor. Let's say a meter stick laying down on the floor. And you kick the meter stick here. You kick it. So what's going to happen to it? It's going to start rotating. Roughly, if we ignore the friction, roughly about the center of mass. So it's going to start going around like that. Okay? So this would be the axis of rotation, the radius of rotation. You see what I'm saying? So we say torque, which has the symbol tau. What does your book use? Yes, tau. The Greek letter tau. The torque here is equal to R cross F, the cross product between the radius of rotation, or the moment arm, sometimes called moment arm, and the force, the applied force. Okay? Another example, let me show you. Let's say take a top view of you are opening the bathroom door. So here's a top view. Here's the door. Okay, remember there's a top view. Here's the hinge right here, right? And here's the knob. Okay, and let's assume that you are pulling the door to open. So now it pulls like here, for example. And you're pulling it in this fashion. Here is the knob. You're pulling it like that. In other words, the force is perpendicular to the door. So if this is the hinge, which means this is the center of rotation, the distance between the applied force, F, and the center of rotation is called the moment arm, R. Okay? And this is the force. So the torque that you have applied, tau, is basically RF. Now, if the force and the moment arm are not 90 degrees, then the torque in this case is RF sine the angle between them. Okay? So if it's 90 degrees, well, sine 90 is 1. So it doesn't matter. So we just RF. Okay? But if the angle is different from that, then you have to so the general rule really is tau equals RF sine theta. And of course, we write it as RF without the sine theta. We are assuming that if the moment arm and the force are perpendicular to each other. Otherwise, you have to use sine theta. Okay. All right. That's one thing. So this torque tau, like I said, it is remember we said that it is the rotational equivalent of force. This is a very good definition. I like this definition. I don't know if it's in your book or not, but that's a good definition. What does that mean? Well, you know that F is equal to the regular force. This is the second law. F equals ma. And we thought that this is called a kinetic reaction. Remember that? What does that mean? It means as a result of the forces on the object, the sum of the forces produce motion. And that motion is accelerated motion, A with M. Okay? And we call that collectively, MA, we call it the kinetic reaction because of the force, because of the sum of the forces. Well, we have something similar. We say that the sigma tau is equal to, well, we have a rotational kinetic reaction. And it's equal to I alpha. So tau equals I alpha. What's I? Moment of inertia. Alpha is the angular acceleration. I believe we did that already. And that's MOI, moment of inertia. Okay? So in other words, we have two versions for the torque. Tau is RF sine phi, or sine theta, whatever. And it's equal to I alpha. Okay? We're going to do some problem next time and show you how those work. Mainly, we're going to be concentrating on tau equal RF. Okay. Please make sure you understand this stuff, especially for those of you who want to take, who are in mechanical engineering or civil engineering. You're going to have to take statics and dynamics. So this stuff, you're going to be using it a lot to solve problems. But anyway, let me give you a quick example about torque. Imagine you have a wrench, okay, and you're trying to, you want to use to turn a knot, okay? So imagine you have a knot. Here is the wrench. I can draw a wrench. I'll make it a little bit thicker. There we go. And then you have a knot here. Here it is. It's hexagonal in shape. There we go. And let's say you're applying a force perpendicular. And here is the moment arm, R. And here is the axis. So this is the angle theta. Let's say 30 degrees. And the moment arm is right here, 20 centimeter. Oh, this is an example in the book. I didn't know that. Okay, so it's example 12.8. Maybe I should show you the picture, probably a better picture than mine. Hold on a minute. Almost done with this video. I'm over an hour now. What's example what? Example 8. 6. Torque. Please take the time to read it. I mean, my advice to you is always read the book before you watch the videos. Because I don't talk about everything. I cannot cover everything in this video. So you really need to read all of that and then watch the video and then watch the video. That's just my advice to you. Anyway, I'm babbling and I missed where the problem is. Sorry about that. Torque, it's got to be here somewhere. There we go. Okay, so there we go. So you have a wrench. He says the angle is negative 120, which is this angle right here. Okay, because it's a clock from. I'm sorry. Here it is. He said Lewis uses 20 centimeter long wrench to turn a knot. The wrench handle is tilted 30 degrees above the horizontal, and Lewis pulls straight down. Oh, okay, so this is the wrong picture. Straight down on the knot on the end with a force of 100, how much torque Lewis exerts, okay? So what you want to do, so my picture is a little bit inaccurate. Let me fix that. Let me just expand that a little bit. So the picture here, so he pushes this dude Lewis. Is that a girl's name or a boy's name? I don't know. Anyway, he pushes straight down like that. So as you can see here, this is the perpendicular position right there. So there is an angle here, and that angle is 30. You see what I'm saying? Okay. So so in this case, we have to, when we calculate torque is RF sine phi, where phi here is the angle between them. Okay. Now, basically, it's a must that R is perpendicular to F. Okay. So your book uses, I like to do it, you know, whether it's sine or cosine, as long as I just want to get the component of the force here, this component. Okay, this component with this moment arm. Well, this component is F cosine 30. You see what I'm saying? So here is my method of doing it. F equals R F cosine 30. So that makes it R is 0.2 centimeter, excuse me, 0.2 meter. F is 100, he said, Newton, times cosine 30 is 0.866. And then you would get cosine 30 is 0.866. So we have 0.866 times 100 times 0.2. Answer, I got 17.3 Newton meter. Okay, that's the torque. Now, because the torque is going in this direction, that's clockwise, it's a minus. Okay, and I don't think it's important, but that's because it's clockwise. So CW, that's a minus. Okay. Now, another way of doing it is that you say, okay, just like he did here, he makes the angle to be, he picks the angle from here to there, this one here. Which I don't think I'm crazy about how he did it. Let me do it with the sine. Okay, I'm gonna forget about how he did it. Let's do it in a different way. Now, we said that this angle when it comes to sine phi, okay, the angle phi is between R and F. That's what it is. Okay. If you don't like the method that I've done it here, you can ignore it. I'm gonna stick with the method of the book. Okay. We're gonna do it this way. Well, where is the angle between R and F? Well, here is R right here. Let me use a different color so you understand what I'm saying. Okay. Here is R right here, right? And here is F. He said he pushes straight down. Well, the angle between them is right there. This is phi. Okay? So in this case, tau is equal to RF sine this angle. This is 30, excuse me. And this is 90, of course. So that must be 60. And of course, we get the same answer. You know, this is cosine 30 is equal to sine 60. And we would get the same answer, 7.3. And of course, it's a clockwise, so you get a minus sign. Okay? Either method is fine. I'm not sure why he does this sine 120. I mean, I guess yet another method, but there we go. I guess he did it here. There's a sine 60 here. But anyway, this is just my method. I don't want to deal with his. Okay? I hope this is understandable for you. To me, as a rule of thumb, the R and F must always be perpendicular. So whether I use sine or cosine doesn't matter. It depends on the nature of the problem. So, or you can just stick with the sine, but make sure that the angle is always between R and F. Got it? Okay. I think I'm going to stop here. And next time, I have several problems to work on from the homework. If you find any problem that is difficult, you can wait until the following week. And I will work, I'm not going to do them all, but I will do a bunch of them, maybe 4 or 5 problems from the homework, hopefully. And that will be basically the subject of next video, okay? In the meantime, please make sure that you read, you know, the whole chapter before you attempt solving problem. I've been getting some emails from students who are having difficulty solving problems. You know, you need to read the whole chapter and you know, practice. You're welcome to ask me a question under Ask the Professor or in the discussion. Any particular problem, I'll be more than happy to solve it for you. Okay? That's it. Have a good day. Bye-bye.